Hello everyone, this is a workshop on acid gas treatment. When we're talking about the sour gas or acid gas, we refer to any other gas that contain some significant amount of hydrogen sulfide, in particular in the natural gas. The sour gas can be treated by MEA methyl-ethanolamine or DEA diethanolamine. This will be in solution, and the treatment will be in an adsorber or adsorption column. In this case, we will have lean amine, which I mean as the pure amine doesn't contain any acid gas, will pass into the column on the top with the concentration depend upon what kind of amine solution is. In case that we are using methyl-ethanolamine, the concentration will a bit low. This is confirmed in the mass fraction. For case of diethanolamine, the concentration will be put in high mass fraction, about 25 to 35 of weight percent. The contractor, which is the one that we will use for the treatment, consists of 20 trays. So look at this, you will see that there are two streams that involve in the contractor. One is sour gas. In this case, the composition will be the composition are nitrogen and acid gas, including carbon dioxide and hydrogen sulfide, and those hydrocarbon from C1 to C7. This one will fit into the column at 1000 psi, which will contact with the DEA lean solution, which has a little bit low pressure to provide some pressure drop from top to bottom. The solution here will have DEA in mass fraction about 28%, which is in this range. According to the volumetric flow rate, comparing between the DEA and sour gas, the mole ratio of DEA and sour gas will be about 10 times. And specification for the contractor will have the pressure drop along the contractor from top to bottom around 30 kilopascal or approximately 5 psi. So which is what we providing here for the pressure in feet. So in this case, the configuration in the primary configuration is sour gas will be checked to make sure that only gas that will go to the bottom of the contractor using flash drum, and then we will have lean amine solution spray down from the top, and the treatment will be in this column. Product in gas phase will be out without any acid gas and called as sweet gas, which will be used for any petrochemical downstream process or anything else. While the lean amine solution, which will absorb the acid gas, or containing the acid gas will be called as rich amine solution. From now, we can go to the simulation. In the simulation, this is a special case because chemicals involved in the system are acid gas, carbon dioxide, acid gas, hydrogen, hydrocarbon, water, and the amine solution. So the simulators provide the right fluid package to use for this case, which called as acid gas here. And after that, you can just input all the chemicals that involved in both streams, stream 1 and stream 2. Stream 1 will be defined as a sour gas, stream 2 defined as a lean one, which you should familiar on that. Now we can go to the simulators. I would like to skip that, how to input the data. So sour gas will have the molar flow rate of about 200 kilomoles, while the lean gas will have the molar flow rate around 10 times of what we have in the sour gas here. Well, now first we will check whether the sour gas contain liquid phase or not. In this case, the Weber fractions is not completely 1, so we have to knock down some liquid out by using the flash drum, and the Weber will to contactor. This one as a liquid we put as a liquid waste. From here, this is for sure that only gas will go to the contactor now. So I put the mixing unit, just prepare for the case of recycle of the diethanolamine for the recycle here. So now we go to the contactor. This is the contactor or adsorber column. Okay. So the one that fit into the top is lean 2, and to the bottom is gas to contactor. Number of trays is 20, and then we call that Weber output in sweet gas. Now this one is rich amine 1. Top state pressure is just what we input here is 970 and 1000. Make sure that this is PSIA. This is as well PSIA. For the case of temperature, this is an optional items. An optional item, so we don't need to use that. I need to replace that. We'll put in run. Okay. Now the contractor is solving. Okay, it is converted now. So we can take a look what happened to the system here in the performance. You can look at here. This is the mole number of hydrogen sulfide and carbon dioxide in the gas to contractor. And when we look at the sweet gas, these two components are gone. This means the absorption is quite efficient. Anything else we can do? Yes, we can plot between the component and we can take a look on the component. Let's see. From here, this is the tray number, and this is the mole fraction of what we are looking for. The color that we are considered as in the blue one and the green one. You can see that the absorber can be reduced. Hydrogen sulfide down by 8 trace. While this carbon dioxide can be reduced by about 10 to 12 or 10 to 12 trace. So to save the oblation, we prefer to have 20 trace. Okay, this is work. So let's go to the next step because we would like to recycle this amine solution back to this part, so we don't have to waste all the amine out. See, we come back to the handout again. The amine solution after absorbed acid gas now become rich amine. The rich amine may be absorb some hydrocarbon gas. What I mean is C1 to C7 from the total acid gas, original acid gas. Therefore, what we need to do is to get rid of those hydrocarbons first before doing the recovery. The way to do is very simple by putting a reducing valve. This can be reduced the pressure down to the point we want. So in this case, I just want very big reducing valve, high different pressure from 1000 psi and down to 1 atm. And after that, the hydrocarbon will be get out from the system. And this liquid will be prepared for the distillation column by heated up, because Later on we will know the boiling point of that. Okay. Now let's go to reduce that. So we put the reducing valve here. This must be rich amine 2 and keep with the pressure of that equal to 14.7. Let's see. Let's put 20 psia. Okay. Now, of course, in this case, after we did reduce the pressure, something will be knocked out. Released for the vapor phase. Of course, that some hydrocarbon. So let's see what it is. What is it? See, you can take a look on this. Some hydrocarbon here and some carbon dioxide and hydrogen sulfide. This we will also treat it later on. So we put the knockout drum put that waste gas, and then this is rich amine 3. Let's see how much we have in the liquid phase. So we check for the waste gas here. Mostly C1 will flow out, but not very much for the acid component. The acid component still in this rich amine. So we do need to separate those out. And before that, we have to prepare by heating up. From here is about 40 degrees Celsius, so we jump from 40 degrees Celsius to 70 degrees Celsius to reduce the load in the distillation column, because we would like to evaporate C7 and water somehow. So we can put the heater, but to do the energy conservation, here we will use heat exchanger instead by using the solution of rich amine that are already purified and ready for the recycle to heat up instead. In this case, we will use a simplified weighted method in heat exchanger design, and let's see, the pressure drop in both streams are at 10 psi. Okay, let's go back. Now what we do is to put heat exchanger here. And of course, the rich amine number 3 here contains some acid hydrogen sulfide solution. This is in liquid phase. So we rather put in the tube, while the lean amine, which is ready for the recycle, will be passed into the shell. So just make that. And this is lean recycle 1. And the output from the tube will be like rich amine to purify. For the shell side, just keep it like lean recycle 2. Okay, and the way to calculate that using simple weighted, specify pressure drop in both sides as 10 psi psi. This is 10 psi. Oh, I think we need to change the pressure here. Should not be at 20 psi. It should be 30 psi. So the reducing the pressure drop can be take place in, because we have to cope the pressure drop inside the heat exchanger. So keep that at 30 psi. Okay. And the temperature here is about 40 degrees Celsius, so we would like to increase to 70. Okay. Now let's go to the parameters. The light key, of course, heptane. Heavy key is water. So let's put that as the specification. And for the pressure here, let's check. The pressure that input here is 140, 177.9 or 137.9 kilopascal, and pressure drop in the distillation column is 10. So what we should put here, that must be 137, and this would be 175. Okay, now the minimum reflux ratio is computed, and then you can see that not much reflux is required. Why? because according to the separation of DEA and C7, they do have very high difference in temperature boiling point, so it's easy to separate. So in this case, we just want to put the safety factor and put the external reflux ratio equal to 1 or 2. Now you can go to see how much, how many trays are required in this case. So about two or three states, not very much, because it's quite simple to recycle, to the fractionate the system. Now let's go to the distillation column. Before going to that, I would like to explain about the specification of this distillation column calculation phase. In this case, we will not use the shortcut for the design, but what we're going to use is to go directly to the whole idea of the distillation column simulation. But however, we need some specification to make the calculation through. The first one, we start with the efficiency of the column. By the efficiency of each tray will be about 0.5 to 0.4 for carbon dioxide and hydrogen sulfide respectively. So where did I get this value from? You can take a look from the efficiency's approximate outcome from the absorption column. And then we will reduce the effect of the oxidation for the calculation. So the damping factor will be reduced to 0.4, and this will speed up the calculation to get to the convergence. Based on this case, of course, we will have the product in vapor. So the partial reflux ratio will not be used. What we're going to use is the full reflux ratio, full reflux. This will help us to get only one product in terms of gas and liquid, or the liquid will return to the system. The pressure drop in the distillation column will be about 10 kilopascal, and the number that given here is from top to bottom will be like this. This is based on the inlet of the feed. And we assume that there is no pressure drop in both a condenser and reboiler. We will have to specify 4 specs. In this case, 2 will be main specifications, and the other 2 will be just initial gas values. Okay, now let's go to connect this. What we're going to use is to use this distillation column, and what I forget to tell you is to number state is about 18, plus the condenser and reboiler will be totally 20. Gas that's come out is, of course, the leached amine to purify, and this would be full reflux. So only gases product will be come out. So I put that at the QC. Of course, you want that, and QR for the reboiler energy uses. And this stream will go to heat exchanger. So this is lean recycle 1. And overhead vapor outlet is called as acid gas. Okay, now we can next go to the next step. Alright, the condenser and reboiler pressure drops will be set 0. And the condenser pressure is 125 as given, and 137 as given as well. We don't know the temperature here, but later on we will use that as the spec, because this is also the optional values, as well as the reflux ratio. So let's go to this one. I think before that, 2 things that we have to do is to go to change the efficiency for each tray. Okay. And by this case, it is fixed for carbon dioxide hydrogen sulfide to be 1, so we change that to be 0.5 and 0.4 for each. So we start from tray number 1, 0.5. No, you don't change that. And for hydrogen sulfide, it's 0.4. These values is based on the equilibrium and the K value, and then go to solving to change the damping factor, and use that as 0.4 to reduce the oxidation. And now we are done here. So let's get back to the specification. In the handout, we talking about this for specification. So let's see the initial gas values first. This just to complete the calculation, so we don't have to activate these 2 values. So they are reflux ratio and reboiler duty. So let's go to do we have that? Yes, we do have this, and the reflux ratio is equal to 0.5. We don't activate that. And then the duty, there is no duty here. Let me delete that. So I add the duty, column duty. Okay, and of course the duty will be take place in the boiler. So in this one, the reboiler duty given in terms of range from 3 to 5, 10 to the power of 6 kilojoule per hour. You can put either number of this. I use that. And then it is inactive. Now let's go to the fixed one. There are two fixed specifications. One is temperature at the condenser, and the other one is to have the vapor product flow rate. And I prefer to have low temperature here because I want the product in gas and also the product flow rate. It is in vapor that what we would like to eliminate are carbon dioxide and hydrogen sulfides. So let's take a look by check at the feed. Okay, we go to check that. Let's see. Based on the molar flow rate, carbon dioxide and hydrogen sulfide is fed into the distillation column around 7.9 plus 3.2. Total is about 11. So that is the value from 11 kilomole per hour. Then we can go to give that value at 11 kilomole per hour and we activate that. Another specification is the condenser temperature. So we add it. Let's check. Okay, column temperature. To add that, it will ask you where it is. It is condenser, and we put that as 45 degrees Celsius. We can do the case study by changing the specification of the condenser here and take a look how much we can get rid of hydrogen sulfide gas. Okay, let's see the summary. And this would be alright. Now we can monitor them. Take a while for the simulation. Oh, very lucky. So in this case, the initial gas is 0.5, but the recycle ratio is quite high. And the overhead vapor flow rate not so far from each other, and this is not so far as well, which is active. However, the duty is quite higher than what we guessed. But anyway, we get the calculation converged. Now let's see how well we can get rid of the hydrogen sulfide. Okay, the inlet contained about 0.0045 and 0.0018, but this is in the mole fraction. So if we change that to the mass flow, you can see that around 500, around 450, 480, 460 kilogram per hour of these two is input to the system of distillation column in the rich amine. After the distillation, after the fractionation, around 400 is out to the acid gas, while the only remaining hydrogen sulfide is only 8 kilogram per hour. So let's see. Okay, if we look at the mass fraction, you can see that not much in terms of carbon dioxide hydrogen sulfide, and this will be about around the input in the lean amine solution at the beginning of the simulation. Look at the flow sheet. We have the stream came out from the bottom at around 110 degrees Celsius, which will be exchanged to preheat the rich amine 3 at 40 degrees Celsius up to 70 degrees Celsius, and that will be reduce the temperature in this line, in the shell line, to 80 degrees Celsius. However, the pressure here is only 68 kilopascal, while the pressure that go to the column is 970. So what we can do is to boost up. Okay. However, let's see the composition here is based on mass fraction. So it's 28 weight percent. How about this one? This is about 28. So I can just go past these direct to the lean solution, lean one here, by just increase the pressure. However, somehow we should provide the water makeup to reduce. We don't need to reduce, so actually we can just do the recycle there. So in case of water makeup water that may be putting some somewhere here, we have to check that water, the composition here will be more concentrated in GEA. So what I mean is some water maybe go out at the acid gas, but not this case. So what we do is to just pump it up using a pump to increase. Not only that, this is the temperature at 81 degrees Celsius, and this is the temperature at 35. So we have to reduce some temperature before adding here. So shall we put some cooler first and some water make up water. So this is just the case. We prepare for 25 and 1 atm with a flow rate of 0. Okay, that will be fed into the mixing unit. And also the lean recycle number 2 will go to here as well. Before going to recycle number 3. And this recycle number 3 will reduce the temperature by passing through this cooling. So lean T3 and then Q cooler and then lean recycle number 4. Okay, there's no pressure drop in this one. And the temperature that we want must be around this temperature, so 35. Put that as 35. 35 degrees Celsius. I don't know how to, rotate this icon. So let's put that lean number 4 out as lean number 5 with some pump duty. And this would be increased to 970. So put that as 970. Yes. Okay, now we have 1700 kilomole per hour, and this is 1748, 47 and 48. So actually, if we would like to recycle that, the initial feed should be less than what we input at the first stage. Okay, now we are about to finish. Only put that into the recycle unit and then go with the lean number 1. I leave that for you to continue. Thank you and goodbye.